In this video I'm going to talk about how to calculate integrals numerically in Python. I'm going to organize the discussion around a rather interesting set of examples, the so-called Borwein integrals. So to introduce these, we're going to look at these functions, fk of x. Start with f0x is sine x over x, and then f1x is 3 sine x times sine x over 3 divided by x squared. F2x, I'm going to have sine x over 3, sine x over 5 divided by x cubed and multiplied by 3 times 5. Or another way I could write it, comes to the same thing. I've got sine x over x, then sine x over 3 divided by x over 3, and sine x over 5 divided by x over 5. If you think about it, you'll see if we reorganize this slightly, we get that. And similarly, the next one, f3, get an extra factor on the end, sine x over 7 divided by x over 7. And then we can carry on as far as we like, but in particular we're going to go up to f7. So f7, you've got sine x divided by, you've got x divided by odd numbers, 1, 3, 5, all the way up to 13 and 15. Yeah, 15 is the last one. So you've got 8 sine factors here, and you're divided by x to the 8, and you're multiplied by 1, 3, 5, 7, 9, 11, 13, 15. Okay, so those are these functions, fk of x, and we're going to integrate them from 0 to infinity. And there's this kind of very strange phenomenon that goes on. That the first 7 of them, I0 up to I6, those are all equal to exactly pi over 2. But the next one is not. It's almost exactly pi over 2. It's equal to this fraction here with a very large numerator and denominator multiplied by pi. And if you take the difference between that and pi over 2, it's about 2.3 times 10 to the minus 11. So there is a conceptual reason why the pattern sort of works the first 7 integrals and then breaks down at the next stage. There's the original paper by Borwein and Borwein that you can search for, which explains why this happens, and there's some details in Wikipedia as well. But we're not going to worry about that for the time being. We're just going to try and evaluate these integrals numerically and check that these claims are true. Okay, but I'm just going to cut and paste these numbers, so we've got them later. We failed to do the imports. Let's do the imports here. I'm importing numpy and pyplot as usual. I could also import scipy with the abbreviation sp. Okay, so here we go. I7 is this answer we're claiming that we get for integral of f7. We see that the differences between that and pi over 2 is around 10 to the minus 11. So the next thing we need to do is to make a Python version of the definition of these functions fk. So we're going to do a basic version first and then do a fancier version. So the first thing, we're going to generate this list of odd numbers. Might as well do it in the numpy form, so it's going to be an np.arange, and we're going to do 1, and then where do we stop? Okay, so the last one here, you've got k is 2, we're stopping at 5, k is 3, we're stopping at 7. In general, we're stopping at 2k plus 1, which means we're stopping just before 2k plus 3. Okay, so we're doing odd numbers, steps of 2, starting at 1, stopping just before 2k plus 3. That's going to be the list of numbers that we want. So then we can do x over m. Okay, so x is probably just a scalar here, and then we divide it by m, which is a vector, so it kind of gets broadcast. And so what you actually get is just the list of these things here: x over 3, x over 5, x up to x over 7, or whatever. Okay, and then because that's a numpy array, we can just apply np.sign to it. Okay, so we take x over m, and then we apply np.sign to that, and then divide by it. Or actually, let's just reorganize that just a little bit tidier. So we're going to do u is x over, so now u is the list of all these things: x over 3, x over 5, x over 7, etc., etc. And so we're going to take sine u over u. Okay, so this is still an array. This is the array consisting of sine x, it's consisting of this term here, sine x over x, sine x over 3 over x over 3, sine x over 5, x over 5. So what we really want is the product of this array. product of all the terms in this list, which we can do by applying prod on the end. Okay, and then yeah, so that's what we want to return. Okay, let's just so we do. We can apply f basic 542. Say that gives me an answer. You can see it's a very small answer. Let's maybe do it with f5 of 2 is 0.4 more or less. Okay, so that's one approach. But okay, let's try it with an array. Okay, it doesn't work with an array. That's a bit of a shame. So it doesn't work as a universal function. That's because what happens at this first step here. We take x and we try and divide it by this array here, and it doesn't really know what to do with that. We need to kind of change the shape of x before performing that division. That's one issue. Another kind of slight issue. It's just a matter of notation, really. But back here, we had a family of functions. We had f2, f3, f1, etc. They're all separate functions with a single parameter x. Whereas here we've got one function with two parameters. If we'd like to make the Python look a bit more like the sort of standard mathematical notation, then we can reorganize it slightly. I'm going to call it fk here. So this is a function that creates a function, which just takes a little bit of getting used to, but it's not. It's just pretty much the same as in the standard mathematical notation. So now the equivalent of this can now be so fk5 is that's just means f5 as we had up here, and then we can apply f5 to 2 or whatever you like. And we need to go back to ignore that. We know that one doesn't work. And then here we have to. I haven't actually executed this yet. Okay, here we go. So now we get the same answer again that we did previously, but we still haven't fixed this issue about arrays. So again, so operands cannot be broadcast together. So all we have to do is just so I think I'm not going to explain this maneuver too much in this video. It is explained in the Jupyter notebook that kind of accompanies this video in more detail. But what we basically have to do, well, maybe just go back to this example here. Let's call this guy x, and then so the effect of expand dims x minus 1, it just puts an extra pair of square brackets around everything in the middle. And now I can divide this by an array, say 1, 10, 100, and it just works in the obvious way. You get a whole bunch of these bunch of vectors of length 3 for each original entry in the array x becomes a vector of length 3, where we divide it by all those things. Okay, so then we have to do that, and then but now this thing this u might have axes in various different directions. and yeah, we don't want to take the product of absolutely all the entries. Yeah, so again, we can maybe do it here. Let's call this y. Now, if I do y.prod, okay, that's not what we want. That just multiplies together absolutely everything in x, everything in y. If I do axis equals -1, now it takes the product of each row. Okay, so that's what we're doing. Okay, so now we've got that's our fk, and this will now work. Okay, let's use this x that we've got here, and we can do fk of 4x. Okay, and so now this these fk's, they work on arrays. Okay, so let's now do some plotting. Okay, so I kind of really want to plot from x equals 0, but x equals 0 doesn't quite work because here we've got all these things where we're dividing by powers of x. And that's undefined when x is 0. So we'll just start from some small positive value instead, and then we'll go as far as 20, and let's maybe have 1,000 steps or something. So we're good. Yeah, and let's maybe look at f6. Okay. So here's the function f6, and let's compare it with f7. Oh, and yeah, the pictures look pretty much the same. Okay, so let's just double check that. So we'll give ourselves two plots. So we'll plot f6 on the left and we'll plot f7 on the right. And yeah, they look pretty much the same. Okay, so why is that? I mean, well, what is actually the difference between f6 and f7? We've put in an extra factor of sine x over 15 divided by x over 15 at the end. Now, when x is within sort of 2 or 3 steps of the origin, say, then x over 15 will be pretty small, and when t is small, then sine t over t is approximately 1. That's kind of one of these standard limiting sort of facts about trigonometric functions. Sine t over t is approximately 1 when t is small. And so in this kind of range, when x is not too big, then sine x over 15 divided by x over 15 will be approximately 1. So adding that as an extra factor between f6 and f7 is not going to change anything. So when x is reasonably small, f6 and f7 are more or less the same. And when x gets bigger, then the difference, then this sine x over 15 over x over 15 term will be, that'll make a difference. Well, it'll be, but both functions are very small at that point anyway, so you don't really see it. Both functions just look like they're 0. Okay, so that's why these two functions look pretty similar. And that should make it at least plausible that all these integrals are actually the same, because the functions are very close to each other. Okay, but so let's try and calculate these integrals. So I'm going to define an integration function. So this is going to find the integral of g from 0 to infinity. So we're basically going to rely on this function sb.integrate.quad. Okay, so that's so quads, short for quadrature. Quadrature is a kind of old name for numerical calculation of integrals. So we're going to do numerical quadrature of the function f. And I'm going to start at 0. Well, actually, yeah, let's maybe again. We'll start at 10 to the minus 14 just to deal with the fact that some of our functions aren't actually defined at 0. So 10 to the minus 14 is about the smallest we can deal with. And then we're going to go all the way to infinity. So here, yeah, np.inf. That's kind of numpy notation for plus infinity. And you know, not all functions will accept np.inf. Some of them will give an error if you try and put in np.inf. But if you read the documentation for this quadrature function, you'll find that it is willing to accept infinity as a limit. Now, I'm going to put in some extra arguments. So I'm not exactly going to explain what these mean here. They're just different ways of requesting that I want an extremely accurate answer, and so it'll be a function will work very hard, calculate lots of points, and try and get the error down as small as possible. Okay, so I'm going to so I'll ask to integrate f4. It gives me this kind of answer here, and actually it gives me a pair of things. The first is what it thinks is the actual integral, and the second thing is its estimate of how close it is to being exactly correct. Because it doesn't actually know exactly what the error is, but has well-motivated ways of estimating how big the error might be. Okay. But here we're getting a warning. There's round-off error. That's because we're really pushing the limits by saying 10 to the minus 14. You can't really calculate it much more accurately than that, and so you're going to get these warnings about how it might not be working exactly right. But so we'll just ignore those. Okay, so we've got. Okay, so let's call the two things the integral and the error, and then so we want to see the claim was that the integral is actually equal to pi over 2. So let's just calculate the difference, and it's equal to pi over 2 with a difference of approximately 10 to the minus 14. So that's good. Okay, so now let's try 5 again, approximately 10 to the minus 14 of pi over 2. And we try it with f6, okay, same sort of deal. Then we do it for f7, and now the difference is about 10 to the minus 11, 2.3 times 10 to the minus 11. Okay, but if you remember, claim was up here, the integral of f7 is not actually equal to pi over 2, but it's equal to this other thing, which we called I7 here. So let's check that. Okay, and so Python agrees. It says that the integral of this function f7 from 0 to infinity agrees with this claimed answer, this enormous fraction multiplied by pi. It agrees with that. With an accuracy down to about 10 to the minus 15. Okay, so I'm going to stop this video here, and then there's going to be a separate video in which we calculate these integrals ourselves instead of relying on the SciPy package to do so, and we examine some of the issues involved in trying to calculate integrals accurately.